So, now we're going to talk about the integral test. We laid the groundwork for, like, this idea showing that, yes, these series are connected to integrals and we can set up pretty easily this comparison between them, like this sum will be less than or bigger than some integral. And then what the whole point of that basically shows that, well, if the sum is going to be less than the integral, and then the integral is equal to a number, then the sum has to be less than a number, which means it converges, is the whole idea. Or we would say, hey, this sum is going to be bigger than this integral. Oh shit, that integral goes to infinity. Oh crap, I guess my sum also goes to infinity and it diverges. Like, you get the idea. It's super technical, the actual thing itself, but the idea is really simple. If your sum is less than a number, then it is also a number and converges. If your sum is bigger than some other thing which goes to infinity, then your sum also goes to infinity and diverges. So let's write out the full statement of it because it's actually a little complicated. Okay. So this only works if the terms of the sequence are all positive. So you can't have... So, like, remember how we said the series is the sum of all the terms in the sequence? You need all the terms of the sequence to be positive, because otherwise stuff cancels out and it's weird. So actually just put... Oh yeah, so if the terms of the sequence are all positive, and there exists a function such that... I have to write this. So, I guess, okay, I'm going to explain this. Your terms of the sequence, you remember how you have a formula for them? And we call those AN? Right, AN is the explicit formula for the terms of the sequence. You need to find a function so that f of n equals AN after some point. After the term a big N. And let me give you an example of what I mean here. Okay, let's say that your sequence is 1, 1, 1, 1/2, 1/3, 1/4, and so on. So the first term is 1. The second term is 2. Or sorry, the first term is 1, the second term is 1, the third term is 1, and then what's the fourth term? 1/2. And then what's the fifth term? 1/3. You would like your function f of x just to be 1 over x. But we're required that a1 has to be equal to f of 1. Now that works out because what's f of 1? It's 1 over 1, which is 1. And a1 is 1. But a2 has to be equal to f of 2. But what is f of 2 equal to? 1/2. But what is a2? 1. So do you see how they don't match right there? But you could rewrite it so that this will match up. And I'll show you how. Okay. A3 is 1. And what you could do is you can make your f of x equal to 1 over x minus 2. Because then f of 3 will be equal to 1 over 3 minus 2. And 3 minus 2 is 1. 1 over 1 is 1. They match. A4 is 1/2. F of 4, you do 1 over 4 minus 2. 4 minus 2 is 2. That gives you 1/2. So you can do it, and your function's a little weird. You had to do 1 over x minus 2. Usually this is not an issue. You just have to be able to do this. You're gonna know that it works if after some point you could just throw away the first couple terms and then use your function. Does that make sense? Like, you don't actually have to figure out this most of the time. You just need to be able to. You'll know that you'll be able to if after some point the terms of the sequence would match up with the function that you would want to use. So I'm just going to erase all that because it's like sort of not important. I just need it as for like illustrative purposes. So if the terms of the sequence are all positive and there exists a function such that f of n is equal to a underscore n, and there's more, f is continuous, or f of x is continuous, the function f is continuous, 2, the function f is decreasing, and 3, the function is such that f of n, I already wrote that, so I guess we'll get rid of this. We'll just put, there exists a function such that the function is continuous, the function is decreasing, and if you plug n into the function, you get the term, the nth term. And this is true after some certain point. Okay, if all those things are true, then this is what the integral test tells you. The infinite sum, the series of the terms in those sequence, and the integral of f of x dx integrated from n, big N to infinity, where big N is the number where the terms agree, where the big N is the number where after that certain point the function agrees with the explicit formula of the sequence. So usually that's 1, sometimes it's not. Fact is, you get some definite integral. So if those 3 things are true, then the series and the integral either converge or diverge simultaneously. So what does it mean for an integral to diverge? It would mean that the integral goes to infinity, right? What does it mean for the series to diverge? It means the series goes to infinity, right? So either, if one of them adds up to infinity, the other one does too. If one of them converges to a finite number, the other one does too. So what do we practically use this for? To figure out whether the series converges, we figure out if the integral converges, because this is an improper integral, right? Do you see how you're having the integral go to an infinity? So guess what? You're now going to have to calculate a bunch of improper integrals. If they converge, then the series also converges. If the improper integral diverges, then the series also diverges. That's what the integral test tells you. Now this only works if the function is continuous, if it's decreasing, and then like the function basically is the same as the formula for the terms of the sequence. Damn, okay, so let's do an example. There's like a lot there, right? So, example. Let's do examples. First example. Let's determine whether this series converges or diverges. The infinite sum from n equals 1 to infinity of 1 over n cubed. So you look at this and you're like, okay, is f of n, if f of x equals 1 over x cubed, you ask yourself, is f of n equal to an? Well, what's f of n? 1 over n cubed. Is an 1 over n cubed? Yes. So you're like, sweet, cool, my function matches, right? Do you see how I've determined that the function I'll use is just 1 over x cubed? If you plug n into f of x, you get 1 over n cubed, which is literally the formula that I'm summing. They match. Okay, so that's the third criteria. Because the third criteria says that you need f of n equal to an. Boom. Yeah, that works. Okay. Is the function continuous? Is 1 over x cubed continuous? Yes, except for at 0. Notice my sum starts at 1, so I don't care about that fact. So then you would put here, this is criteria 3 satisfied. Okay, we know that f of x is continuous on 1 to infinity, right? Because its discontinuities are at 0. The 1 to infinity comes from the fact that I'm summing from n equals 1 to n equals infinity. So yes, it is continuous. So that's criteria 2 satisfied. Now what's criteria, actually, wait, f of x being continuous, that's criteria 1, my bad. So criteria 1 is satisfied. Okay, now what's criteria 2? You need the function to be decreasing. If you really wanted to show that this was decreasing, what would you do that you learned about in Calc 1? How do you know if a function's decreasing? You would show that the derivative is... How do you know if a function's decreasing? The derivative has to be what? I know it's been a while, but how do you know if a function is decreasing? It's negative, yeah. And this is actually not that hard to do because this is, the function is x to the negative 3, so if you take the derivative, you get negative 3 over x to the 4th. X to the 4th will always be positive. The negative 3 makes it always negative, so it's negative, so you know that f of x is decreasing. And boom, criteria 2 is satisfied. Criteria 1 is satisfied, the function is continuous. Criteria 2 is satisfied, that the function is decreasing. We know that because the derivative is negative 3 over a positive number, so that's always negative. And criteria 3 is satisfied. This is just the, if you plug in n, you get the formula for a over n. So, because all three things have been satisfied, we can now use the integral test. So what are we going to do? Well, we are going to now calculate the integral from 1 to infinity of 1 over x dx. Now this is an improper integral, so we're going to do the limit as b goes to infinity of the integral 1 to b x to the minus 3. Which means the limit as b goes to infinity of, now we work on this, what's your antiderivative? Antiderivative says add 1 to the power. So you're going to get x to the minus 2 divided by minus 2, right? Okay, and then now I need to calculate f of b minus f of 1 from the fundamental theorem of calculus. Okay, we're going to have to plug in those numbers. So I'm still doing the limit as b goes to infinity of... Okay, so what can I factor out from f of b and f of 1? I'll be able to factor out the minus half. Right? Okay, which means I'm going to get 1 over b squared minus 1 over 1. So I'm going to move that minus 1/2 out in front. I'm going to take the limit as b goes to infinity of 1 over b squared minus 1. What happens to 1 over b squared as b goes to infinity? Well, that's just going to go to 0, right? So you're like, okay, cool. That means that this limit is going to be negative 1/2 times negative 1, which gives you positive 1/2. If you integrate this function from 1 to infinity, you get 1/2. In other words, yay, the integral converges to 1/2. Now, since we satisfied the 3 criteria of the integral test, we know that the series and integral both converge or diverge. The integral converges, thus, so does the series. Yay! That series converges to something. Very important. You don't know what it converges to. It does not necessarily converge to 1/2. And in fact, that's why I showed you that example earlier. Do you remember how I showed you that the sum of the rectangles was going to be different than the area under the curve? Even though they were both, the formulas were the same? You can't say that the series is going to converge to 1/2. It just converges. That's all you know. You don't know what it converges to. This only tells you that it does converge. You don't actually know what it converges to. Very important difference.